standing by my side. Pretty girl and shiny Buick fills a fella with so much pride. Driving down the road on Sunday with my car and my heart riding high. For I know that very soon we'll take a honeymoon, my Buick, my love and I.
Gasoline. We use it every day and just take it for granted. But all it takes is one tank of contaminated gas to strand you on the side of the road or leave you stuck in your driveway to change your view of gasoline forever. As Buick technicians, you ought to consider fuel as an integral part of the fuel system whenever you diagnose a drivability concern. And that's what this know-how is all about. You'll learn about the recent changes in gasoline and what's been changed in the fuel delivery system. You'll hear about some quick ways to get to the root of common drivability symptoms. We're going to do this by speaking with 3 drivability experts from the Buick Motor Division. First, let's speak with John Fletcher. John is one of Buick's resident service engineers for drivability, and he's going to help guide us through the changes in fuel and fuel systems. Hi, John.
Hi, Chuck. Thank you. It's a pleasure to speak for Buick in this know-how program. I have a lot of information I'd like to share with you about today's gasoline. In general, fuel is made up of light ends, middle ends, and heavy ends. Light ends evaporate the quickest. That helps start cold engines and promote good cold drivability. Middle ends contribute to vapor lock control and good hot drivability, while the heavy ends have the highest energy content of the 3 groups. As far as the major brands are concerned, differences between gasoline are only identifiable by the pump octane number. The research method will test the fuel's low to medium RPM anti-knock resistance. The motor method will test the fuel's part throttle and high RPM anti-knock resistance. The average is what we see on the pump. Most Buick engines operate on regular unleaded 87 octane fuel. The Series 2 supercharged 3800 engine requires at least 91 octane. If a vehicle is operated at a high altitude, say on a high mountain pass in the Colorado Rockies, the octane requirement may drop. Atmospheric pressure is lower at higher altitudes, and the actual compression in the cylinder is lower. That's why you may find 85 octane fuel in these areas instead of the 87. Now let's talk about fuel's volatility. Volatility describes how fast a fuel changes from a liquid state to vapor. The rate of change has a tremendous impact on drivability. In the cold, you need fuel with a higher volatility for cold starts and good cold drivability. In warmer areas, lower volatility is better to prevent excessive evaporative emissions, vapor lock, and hard start concerns. Oil companies produce winter and summer blended gasolines. Drivability concerns arise when oil companies shift from winter to summer fuel in mid-March and mid-October. If a vehicle is using winter gasoline and the temperature is unseasonably warm, vapor lock may occur. The other side of that is if you are using summer blended fuels and the temperature turns unseasonably cold, you could be faced with a cold startability problem. We're facing a problem in many areas today with carbon monoxide. A winter oxygenated fuel program addresses this issue. Here's how oxygenated fuel works. Oxygenated fuel was mandated by the EPA several years ago, and it's now being used on a widespread basis in dozens of major metropolitan areas across the country in the winter months. Ethanol and MTBE are gasoline additives that contain oxygen. These additives are blended with the base gasoline to add oxygen to the fuel. When combustion occurs, the carbon monoxide and oxygen form carbon dioxide. When oxygenated fuels first appeared, the energy content was almost 30% less than base gasoline. Because the oxygenated fuel didn't produce enough heat energy for the engines to run well, there were starting problems, stalling complaints, and reports of poor fuel economy. As oxygenated fuels improved, these complaints decreased. Buick encourages the use of oxygenated fuels, but we don't favor all additives. Methanol is one additive to avoid. In fact, for 1996, the use of gasoline with methanol is strictly prohibited by General Motors. Methanol destroys plastic fuel lines and fittings and is harsh on the fuel system's electrical components. Using methanol can void the 1996 new car warranty. Another concern is the use of MMT, an octane enhancer. Problems with MMT surfaced in the late 70s. MMT was banned in 1978. However, MMT is still used today in Canada. MMT increases spark plug fouling and misfire, increasing HC emissions. On OBD2 cars, oxygen sensor readings will be altered and codes may set. The EPA has mandated reformulated gasoline for other areas of the country with ground-level ozone problems. Hydrocarbons escape into the air at the pump, from the evaporative emission system, and from the tailpipe. Hydrocarbons and nitrogen oxide form ozone in the presence of sunlight. If fewer hydrocarbons escape, less ozone can be produced. To accomplish that, oil companies change gasoline so that it doesn't evaporate quite so easily. Vapor pressure has been about 9.0 since 1992, but in 1995 it is down to 8.1 in the northern United States and 7.2 in the southern areas. I just want to mention that beginning last January 1995, all gasolines were required by law to have detergent additives to prevent, and in some very limited cases, clean fuel deposits from the intake valves. However, GM does not recommend any consumer-added products to the fuel tank. That should do it for gasoline changes. Now let's take a look at some of the fuel system component changes, starting with the fuel pumps. Some of our new fuel pumps are what we call modular systems. A modular system includes a bucket, a cap with fuel lines, a fuel pump, a fuel level sending unit, and a fuel pressure pulsator or convoluted tube. Some modular systems are for unit replacement. Other systems are designed so that just the fuel pump can be replaced if you run into a low fuel pressure problem. Current fuel pumps include the Gen 2 twin turbine, Gen 3 twin turbine, and the roller vane fuel pump. Fuel injectors have been redesigned too. Stainless steel components combat water and alcohol in the gasoline. If fuel with excessive alcohol passes through an injector, the coil insulation may be damaged, allowing water and alcohol to enter and short the injector coil. Bosch-style injectors use an orifice and movable pintle design that is very susceptible to deposits. After the engine is shut off, fuel remains on the pintle and can sometimes leak past the pintle seat due to remaining fuel pressure. Engine heat literally bakes fuel onto the pintle. Small deposits significantly restrict fuel flow and alter the injector spray pattern. Newer Maltec fuel injectors avoid this by using a check ball instead of a pintle. Furthermore, the ball and seat are housed inside a stamped steel shell. The steel shell determines the fuel spray pattern and shields the injector tip. This means injector deposits are virtually eliminated for the new Maltec fuel injectors. Since Maltec injectors aren't susceptible to fuel deposits, do not use injector cleaner. Injector cleaner damages the insulation, which leads to coil failure. Injector cleaner also reduces the fuel's lubricating quality at the metering orifice, leading to premature wear of the ball and seat assembly. Valve sticking is a recent wintertime fuel concern that occurs after an engine is shut off. If the fuel has excessive detergent and ambient temperature is about 20 to 30 degrees Fahrenheit, residual fuel on the valve stem can turn into a sticky varnish type substance as the engine cools. The valve stem and guide stick together. In some cases, push rods have been bent. Another fuel problem is the formation of intake valve deposits. Deposits can be caused by poor quality fuel or an incorrect ratio of fuel and detergent. Driving habits can affect deposits too. Stop and go driving, extended periods at idle, heat soak, and engine temperature also affect deposits. Hesitation, stalling, increased fuel consumption, and exhaust emissions may result. Deposits collect on the backside of the intake valve after the engine is shut off. Lighter hydrocarbons evaporate, leaving a residue behind. Valve deposits absorb fuel on startup, contributing to stalls and poor cold drivability. Contrary to advertiser claims, not all valve deposits are easily removed with gasoline. You can also use GM top engine cleaner. Start the engine, and while it warms up, push the end of a clean funnel into a length of hose. Shut the engine off and disconnect the brake booster vacuum hose from the engine. Connect the hose and funnel to the brake booster hose connection. Pinch the hose shut and start the engine. Raise the RPM to a high idle. Slowly pour the cleaner into the engine. You'll need to compensate the throttle to keep the engine running. When the can is about half empty, release the throttle and pour the remaining contents into the engine. This should stall the engine. Now the cleaner goes to work on the deposits. About 15 minutes later, start and run the engine until the exhaust clears up. If the top engine cleaner didn't do the job, heavily deposited valves must be removed from the head and physically cleaned with a wire wheel. This next situation concerns the 3800 and Series 2 3800 engine. Any water in the tank can be pumped into the fuel rail. Water tends to collect at the fuel pressure regulator area, resulting in a fuel-related misfire. Remove the rail and injectors and pour the fuel into a container. Invert the rail and mildly strike it to remove any trapped water from the injector. Now we're going to talk about the fuel delivery system and fuel, as they both relate to certain drivability concerns. John Cianchi is our SDM for the Dallas zone. John is going to take over and lead us into the drivability diagnosis area. Hi John, glad you could join us today.
Thanks, John. Well, I might as well jump right in. You know, a fuel component or even fuel can cause drivability problems such as hot hesitation sag, cold hesitation sag, cold or hot hard restart, hot restart stall, and rough idle. A hot hesitation sag is a momentary lack of throttle response that can occur at any vehicle speed. This symptom is more noticeable when the engine is hot, just as the driver tries to pull away from a stop. If it's severe, the engine could stall. The first thing you need to check is fuel pressure. Use the J34730-M fuel pressure gauge. Connect the gauge to the fuel rail. An easy way to check pressure is to just ground the fuel pump connector for a few seconds. Bleed the air from the test gauge into an open container. This gives you a more accurate reading. It should hold within a few pounds for 15 minutes. If not, check the fuel pressure regulator and then the fuel pump. Keep in mind that after shutting off a very hot engine, fuel pressure rises. A static test doesn't help you determine if hesitation or sag is caused by a drop in fuel pressure, so you'll have to drive the car and watch the fuel gauge while accelerating. If the car hesitates or sags, see if you also get a drop in fuel pressure. Confirm this with the Tech 1. On acceleration, the oxygen sensor shows a lean condition if the reading is 450 millivolts or less. At the same time, if the fuel injector pulse width is above 3.5 millivolts, there's a problem. Injectors commanded on continuously should not produce a lean condition. Next, check the fuel. Fuel with high vapor pressure can boil in the rail and injectors, causing a fuel-related miss. Test the vapor pressure of the fuel using the procedures in the reference manual. If the fuel's okay, check the injectors. We'll use the J34730-E Port Fuel Injection Diagnostic Kit. Now this kit's been around for a few years, but I still hear from techs who just aren't sure how to use it. The J39-021 Fuel Injector Tester performs a voltage drop test instead of reading resistance. This test must be performed when the engine is between 50 and 95 degrees Fahrenheit. We'll need a Tech 1 to tell us this information. The engine needs to be in this temperature range because temperature affects resistance, which affects voltage. Connect the tester leads to the injector and then attach its power leads to the battery. Connect the J39-200 Fluke-meter leads to the injector tester. For this Series 2 3800 engine, set the amps knob to the 0.5 setting. Set the voltmeter to the 10th scale. What you want to see is stable or slightly increasing readings. Press the Push to Start Test button and watch the meter. Make sure to note any erratic readings. Write down the lowest reading 1 second after pressing the test button. Then repeat for each injector. Replace any injector that is not between 5.7 and 6.6 volts. If the engine is either below 50 degrees Fahrenheit or above 95 degrees Fahrenheit when the test is performed, look for stable readings under 9.5 volts. Identify the injector with the highest voltage reading that is less than 9.5 volts. This one is 9.4, so it's our standard. Subtract the voltage reading from all injectors that read less than 9.4 from 9.4. Then look at the differences. Anything more than 0.6 of a volt means that the injector needs replacing. Also, replace any injector that is erratic or reads above 9.5 volts. Injectors that pass the coil test need to undergo an injector balance test. Now, we still have our gauge and injector tester connected. For this engine, set the balance test amp switch to the 0.5 to 2.5 setting. Turn the fuel pump on and then off to pressurize the system. Write down the fuel pressure. Press the Push to Start Test button to rapidly fire the injector. This depletes some of the fuel pressure. Note the fuel pressure when the test stops. Repeat this on the remaining injectors. When you're done, subtract the low pressure readings from the high pressure readings. That tells you the pressure drop for each injector. All pressure drops should be within 1.5 psi of each other. If an injector has a difference of 1.5 psi or more, retest it. If it fails again, replace it. Next, let's look at a cold hesitation sag concern. Cold and hot concerns are similar. Both can be related to fuel pressure, but a cold concern is also sensitive to temperature. So check fuel pressure first, like we just did. If fuel pressure is okay, check a few Tech 1 readings. When the engine is cold, the coolant temperature sensor should be within 2 degrees Fahrenheit of the intake air temperature sensor. Short-term and long-term fuel trim should not be too high or too low in open loop. The TPS readings must be within specification. It should be less than 1 volt with the throttle closed and about 4 volts at wide open throttle. Map voltage should be between 1 and 2 volts when the engine is idling at operating temperature. Then check service bulletins for any PROM or MEMCAL updates that might affect the car you're working on. Perform an injector balance test just like we did a few minutes ago. Now I'd like to introduce Barry Sigmon, a fellow service development manager from the Atlanta zone. Barry, why don't you take it away and wrap this up?
Thanks, John. I guess I'll begin with a cold or a hot start drivability concern. If you get a symptom like this, you'll probably be cranking the engine for a long time before the engine actually starts. Sometimes the engine will start and then immediately stall. Check the battery voltage. The source is probably low fuel pressure. So perform the fuel pressure and fuel injector balance test that John showed us about 5 minutes ago. Use a Tech 1 on a cold engine to check the coolant temperature sensor and the intake air temperature sensor readings. They ought to be within 1 or 2 degrees of each other. The throttle positioning sensor must be within range with no dead spots or dropouts. Map voltage should be between 1 and 2 volts when the engine is idling at operating temperature. The vehicle should be equipped with the most recent PROM or MEMCAL update. This can be checked by reading the service bulletins. One of the most important things to check are the PCM grounds. I know we keep saying this, but if you have a loose ground, anything can happen. Clean and tighten all PCM grounds. Something that you always have to keep in mind is the ignition system. Ignition problems create symptoms that are almost identical to fuel system problems. Since we want to concentrate on the fuel system, let's rule out the ignition system. Check the crank sensor signal. A weak signal can prevent the ignition module from sending the 3X or the 18X signal to the PCM. The crank and cam sensor inputs can be tested using the connector test adapter kit J35616 and chart A3 in the Buick service manual. Then with the Tech 1 connected, check for a possible loss of the IAC signal. Use the Tech 1 to command the IAC motor to move. If the idle speed changes, you know the pin will move. If the IAC doesn't react, inspect the wiring and connectors and repair as needed. If the wiring and connections are okay, replace the IAC motor. Next, use the ST125 to check for a possible weak secondary spark. After that, use the fuel test kit to check for water or excessive alcohol. Excessive alcohol may have caused injector coil damage in 1 or more injectors. Low reed vapor pressure fuel contributes to cold starting trouble if the fuel is not volatile enough to burn in the cylinders. Perform the reed vapor pressure test in the reference manual. Finally, consider intake valve deposits. As John mentioned earlier, intake valve deposits soak up fuel when the customer is trying to start the engine. Brand new cars using new detergent fuel shouldn't have this problem. However, if a car is even 1 or 2 years old, the valves may already have deposits. If so, the valves will have to be removed from the head and physically cleaned with a wire wheel. A hot restart stall symptom means that a hot engine may start then immediately stall. Once again, check fuel pressure during a hot restart, using the same fuel pressure testing techniques outlined earlier. Then connect a Tech 1 and see if the IAC signal is okay, just like we did in the previous symptom. Test the fuel for a high reed vapor pressure reading using the test outline in the Know-how reference manual. Fuel with a high reed vapor pressure reading can boil in the fuel rail and injectors. If the fuel system's okay, check the EGR valve using a Tech 1. Is the EGR valve opening during startup? If so, it's leaning the air-fuel mixture excessively, causing the hard start concern. Finally, check the ignition system as we outlined for the previous symptom. With a rough idle concern, the engine idle can be so unstable that the vehicle may shake. Idle speed may vary quite a bit. This condition may be so severe that the engine could stall. With a Tech 1 connected, check for a misfire related to just one cylinder. Long-term fuel trim should not be too high. 0 is the baseline figure. A rich condition is noted by a negative percent figure. A lean condition is noted by a positive percent figure. The range is from a minus to a plus 10%. The Tech 1 can also let you see what the PCM is commanding the IAC to do. You can override the PCM command to see if the IAC is working. Check the complete ignition system as referred to in chart A3 of the 96 Buick service manual. Then perform a fuel pressure and fuel injector balance test as outlined earlier in the program. Check for vacuum leaks at the intake manifold and other areas that are susceptible to leaks. An ultrasonic tester works well for this. The next step is to check cylinder compression. As you know, do this with the engine at operating temperatures, all spark plugs removed, fuel and ignition disabled, and the throttle plate held open. Crank the engine over only 4 times. Record the highest reading. Here's the difference. Repeat the test 4 times before going to the next cylinder. A reading that starts high but goes down with each compression stroke indicates a burned valve. Check the engine to be sure it has the correct PCV valve and that the entire PCV valve system is working. Here's another one. Something as basic as a weak valve spring can cause rough idle. Let's use this VNL 3800 engine for a better view. Rotate the engine to close each valve. From the cylinder head to the bottom of the spring cap should be 42 to 44 millimeters. If the spring height is more than 44 millimeters, the valve has been ground improperly or the valve seat is worn enough that the valve stem is being pulled higher by the valve spring. That requires a valve job. If the cylinder has good compression, the valve is probably okay, but the spring may be weak. Valve spring shimming up to about 1/16 of an inch is allowed to restore spring tension. And that's how you take care of these drivability concerns. You just have to ply your way through the possible causes to get to the real cause. And since the PCM does such a good job of compensating for components that are failing, this can be very difficult. But I know that finding the actual cause is pretty satisfying. And remember to use the Know-how reference manual.
Thanks, Barry. On behalf of the Know-how team, we really appreciate you coming here to share your expertise with us.
I enjoyed it.
Now there's no way a fuel problem should sneak past you.